Okay, for this video, I'll be going through pure physics energy. Okay, success criteria C. State the principle of conservation of energy and apply the principle to new situations or to solve related problem. Now, this is the principle of conservation of energy. It states that energy cannot be created or destroyed and can only be transferred from one store to another. Now, the total energy of an isolated system is constant. Okay, so if this comes out in O level, when they ask you to state what is the principle of conservation of energy, it will usually be 2 marks for O level. So this first bracket is the first mark. Okay, followed by the total energy of an isolated system. This statement is the second mark. Okay, now to illustrate the principle of conservation of energy, we use an ideal pendulum swinging in the absence of air resistance. That means for this ideal pendulum, it will forever be swinging, but in real life, it will not be so. Okay, so how do we start off with? The pendulum bob is displaced to position A, so we bring it up to a height. So at this position, it will have energy in the gravitational potential store. Right, so it is at height x above the horizontal level. Horizontal level is where at B the pendulum stays stationary. So at position A, the amount of energy in the gravitational potential store is the maximum due to its height x. Let's say we bring it up to this height x, we have maximum energy in the gravitational potential store. Okay, but over here at this position, it is not moving, so V equals to 0, so the EK equals to 0. Okay, so when we release it, it will swing downwards with an increasing speed due to accelerating resultant force of its weight and tension. So as the height x decreases to 0, right, the energy is transferred mechanically from the gravitational potential store at A to the kinetic store at B. Okay, and now we apply the principle of conservation of energy because energy cannot be created or destroyed. So the energy in the gravitational potential store is transferred to the energy in the kinetic store. Okay, so when it is at position B, okay, because the height is 0, therefore EP equals to 0. And because all the energy has been transferred from the previous position where it has maximum maximum energy in the gravitational potential store, so now it has maximum energy in the kinetic store. Okay, so we can say that it is actually equal to it. Okay, and therefore the velocity is maximum. Okay, so it has a maximum speed when it reaches B. Okay, now the pendulum of course won't stop there, it will swing upwards. So it will swing to position C, and because this is an ideal pendulum, it will be displaced to the exact same height as it was initially displaced. Okay, so it will go up to this height x. And again, we see the transfer of energy from the B's kinetic store. Okay, it will then be transferred to the EK at B is being transferred to the energy in the gravitational potential store of C. Okay, so how do we represent it in a diagram? So example, we have this 5 units of energy in the gravitational potential store when it is at position A. Okay, so the system is this ideal pendulum. So when it's at B, okay, it will actually have this same 5 units of energy, but now it has been transferred to the kinetic store. And if we were to continue, so at position B, we have actually 5 units, right? And we are still talking about this ideal pendulum. So this energy will be transferred to the energy in the gravitational potential store when it is at position C. Okay, so we find that we start off with 5, it ended off with 5 as well, meaning no energy has been transferred to the surrounding. Now this is the ideal pendulum, but because ideal pendulum, it is not really ideal. Okay, because in real world we have presence of air resistance. Okay, so if I am to now talk about in real world pendulum. So we displace the same pendulum, okay, to a height of x. Similarly to just now, to position A, okay. So there will now be energy in the gravitational potential store, but when we release it, right, let's say we have 10 joules, just to give it some numbers, okay, there will be energy transferred mechanically to the internal store of the pendulum bob and the surrounding. So basically these are the energy in the internal store, okay, and what is left is only 8 joules of energy in the kinetic store being transferred to the kinetic store of the pendulum, okay. And then this is from A to B, and from B to C we will see that, let's say we also have the same energy that's being transferred mechanically to the internal store of the pendulum and the surrounding. So again, we just minus these 2 joules. We will actually end up with a lower energy in the gravitational potential store for C. Okay, so 8 minus 2 will become 6. And if we were to continue, then it will go from C to B. So again, from 6 joules, it will become 4 joules. Now, where did the other 2 joules go to? It is again transferred to the internal store of the pendulum and also the surrounding. So eventually, it will end up with 0 joules. Okay, the amount of energy in the stores of the pendulum will become 0, and it will then be in this position where this is the reference height. Okay, so the height is 0 and velocity is 0. So eventually the total energy of the pendulum in its stores will become 0, and therefore it will come to a stop. But if we were to consider the pendulum and the surrounding as the whole system, the total amount of energy in the energy store of the pendulum and the surrounding remains constant. So eventually, it will have 10 joules, okay? The internal store of the pendulum plus internal store of the surrounding. Okay, so let's try to apply. So before that, it is more like the explanation question, description. So again, you must talk about the transfer pathways, how the energy is being transferred from store to store. You must talk about from what store to what store, and you must also mention who is the owner of the store. Okay, so let's look at C1. Figure below shows a simple pendulum which swings from A to B to C. Pendulum bob has a mass of 20 grams, so this is M, and because you know that it's going to be in SI unit, so you have to convert it to 0.020 kg. Okay, now the bob is released from position A. Okay, so this is the starting. Calculate the change in energy in the gravitational potential store of the bob when it swings from A to B. So we take position B as the reference, right? And we see that A is actually at a height of 15 cm. So if we were to convert it to SI unit, the height will be 0.15 meters. Okay, so over here it has maximum energy in the potential store. Over here, because this is the lowest height, the reference height, so it has 0 energy in the potential store. So they ask us to calculate the change. So the change in EP will be just mgh. So it will be 0.02 multiplied by 10 multiplied by 0.15. So the answer will be 0.030 joules. Okay, now state the energy in the kinetic store of the bob at position B. So we have learned in the previous example for the ideal and non-ideal, the energy in the potential will be transferred to the energy in the kinetic store. So kinetic store will have 0.030 joules at B. Okay, now calculate the speed of the bob as it passes position B. So we can use this formula, EK equals to half mv square. Okay, and our EK is 0.030 equals to half. M is still the same, 0.02, and V square. Therefore, our V will be equal to 1 1.73 meter per second. Okay. Now, when the bob swings up towards C, it reaches a maximum height that is lower than position A. Okay, explain why the bob is unable to reach the same height as position A. So, before this, they were just saying that it is a simple pendulum. It doesn't say that whether it's ideal or not. So, so through this, we know that this pendulum is actually not an ideal one because it didn't manage to reach the same height as A. Okay, so there is going to be work done against friction and air resistance. Okay, so some of the energy in the kinetic store of pendulum is transferred mechanically to the internal store of pendulum and surrounding. Okay, so therefore it will have lesser energy being transferred to the gravitational potential store. Okay, so C2, a ball rolls up a frictionless slope to come to rest before it rolls down. So that means as it goes up the frictionless slope, the velocity decreases, okay, but the height increases. Now, which of the following graphs shows the correct energy in the kinetic store and gravitational potential store of the ball during the up motion? Okay, so when it goes up, the velocity decreases. That means I should see my KE decreasing, or energy in a kinetic store decreasing. But for D and B, the K energy in the kinetic store is increasing. So definitely they are out. Okay, and just to check my gravitational potential store, because it's going up, so as height increases, EP will increase. So yes, EP increase, EP increase. All right. But there were some students who were asking why is the answer A and not C. Okay, so I actually come up with this quick explanation. Okay, so at maximum height, EK is 0, EP equals to mgh. Okay, so if I were to just maybe separate it into 4 different stages, when it is at the bottom, and when it's 1/4 height, half height, 3/4 height, and h. Okay, so I then do my calculation like that. Okay, and that is when I apply principle of conservation of energy, no energy being transferred to the surrounding. So I can then plot a very nice graph, okay, to show that actually it changes linearly. Okay, so you may want to take a look at this. Okay, question C3, a block of mass 3 kg, so this is my M, was held at rest. That means V equals to 0. That means EK is 0. In position A, and it's 2 meters above the ground. So this is my height. Everything is in SI unit. Take G to be 10 Newton per kg and ignore the effects of air resistance. So I don't need to care about energy being transferred to the internal store of the surrounding. Okay, so there is no energy transferred to internal store of surrounding. Okay, they want us to calculate at position A the energy in the gravitational potential store. So this one is easy. EP equals to mgh. So equals to 3 times 10 times height, which is 2. So it is 60 joules. Okay, so state the energy in the kinetic store. Because V equals to 0, therefore EK equals to 0 joules as well. Hence, calculate the total energy in both kinetic and gravitational potential store at position A will just be 60, right? So now the block was released and hits the ground. State the energy in the gravitational potential store. When it hits the ground, the H is 0. Therefore, EP equals to 0 joules. Now state the energy in a kinetic store, okay, because the energy has been transferred to the kinetic store, right, just before hitting the ground. So EK equals to 60 joules. Hence, calculate the speed, okay, upon impact. So we can use EK equals to half mv square. So EK is 60 equals to half. The mass is 3 v square. So therefore, v will be equals to 6.32 meter per second. Okay. Okay, C4, a block of mass 3 kg, so M3, was dropped and at position A, 2 meters above the ground. Okay, this is H. Its speed was 20 meter per second. Okay, compared to just now, whereby the block had 0 speed at A. Okay, so the height is still 2 meters if you were to compare. So that means there's going to be energy in EK, right, because there's speed, and there's also energy in EP because there is a height. So G is still 10. And again, we ignore the effects of air resistance. So at position A, calculate the energy in the gravitational potential store. So everything is the same as before, so it's 60 joules EP. But now, what is different is that at A, now it has a velocity of 20. So I can actually calculate EK. So it used to be 0 because the speed was 0, but now it is not. It is 20. Okay, so the answer will be 600 joules. Okay, so what's the total energy? Will be 660 joules. And it continues to fall and hits the ground. State the energy in the gravitational potential store. Okay, so it will be 0 joules now. So what's the energy in the kinetic store? 660 joules, right? Because both the energy in the at A, right, we have both EK and EP. So when it hits the ground, it is still a sum of these two. Okay, just that there will be more energy in the EK. So they ask us to calculate the speed. Okay, so EK just now was 600, EP was 60. So now EP equals to 0 at the ground level. EK is 660 joules. Okay, so we can again use EK equals to half mv square. So 660 equals to half times 3 v square. So now our v is 21 meter per second. Okay, so actually the velocity increases from 20 to 21. So alternative method using VT graph. Okay, so actually there's this alternative method that you can use a VT graph. So I have sketched out a VT graph. So the initial velocity is 20, right? So after certain time t, when it hits the ground, so this is when it hits the ground. Okay, we are supposed to find the final velocity, the velocity upon which it hits the ground. Okay, so we know that the area underneath the graph is the distance traveled, which is equals to 2 meters, and we know that the gradient of this VT graph is 10 meter per second square, right? Because that's the acceleration of the object. Okay, so having drawn your VT graph, then we can use VF equals to U plus AT, right? Because there is a certain acceleration, so it's equals to 20 plus 10t. Okay, next thing we use area under the graph is 2 meters. So then we can use our area of trapezium, which is half times parallel sides, okay, which is 20 plus VF multiplied by the vertical height, which is T, and is equals to 2. Okay, so if we were to simplify this, or in fact make it even more complicated, we'll get this quadratic equation, 5t squared plus 20t minus 2 equals to 0, and solving we'll get t to be 0.097 seconds. Okay, so actually it took about 0.097 for this block to fall 2 meters. So how do we get the final velocity? We sub back into Vf equals to u plus at. So the final speed is u plus at, which is 20 plus 10 times 0 0.097. So we also get the answer of 20.97. Okay, so this is 21.0 in 3SF, okay, meter per second. Okay, now how about we use a kinematics formula? Okay, so what are the kinematics formula that we can use? We have v squared equals to u squared plus 2as. Let's see if we can solve this. So v squared is the unknown, right? U squared is 20 squared. 2, the acceleration is 10. Distance traveled is 2. Okay, so it will be equals to 400 plus 40. So this is our final velocity, and therefore Vf equals to, you square root both sides, 440. You should also get 21.0 meter per second. Okay, so this is alternative method.